Hello everyone, I hope that you are fine. Welcome to another lecture of robotics. In previous lectures, we have studied different techniques for path planning. We have seen that there are different types of algorithms and each algorithm has their own plus and minus points. So, in this lecture, we shall continue to discuss some more topics related to path planning. So the first thing is path smoothing or smoothing. In the previous lectures, you have studied algorithms such as Dijkstra's algorithm, A-star algorithm, which uses this grid or cell-based planning. And then we also studied RRT algorithm, in which we studied that how randomly samples can make a tree and then we can make a path out of it. If you have practically implemented it, the RRT algorithm, you must have noticed that the path was not smooth. There are always some corners, some edges, and so the problem is that when the robot follows this kind of zigzag path, for example, if the path from the RRT is like this, for example, so you can see that this is the start point and this is our goal point here, and you can see the path is not smooth. It's like there are a lot of corners and edges there. So when the robot follows this kind of path, there will be a lot of jerks in this motion. Okay, to solve this problem, what we do, we use this technique called subdivide and reconnect. And how it works is, let's take a jerky path again. So let's say this is our start point, this is our target point. So what we do, you know that the path, it consists of nodes. If the path comes from A-star, Dijkstra or RRT, it must consist of some nodes. This was a starting node, and then we have a second node here, so these are the nodes, or you can see also the waypoints within the path, and this is your finally the target one. So this technique, and of course this path is not smooth, and let's make an obstacle here. So let's say we have an obstacle here. Okay, so this is an obstacle, and now this technique subdivide and reconnect. What this technique does is that it takes any 2 points on the path randomly, okay, and it connects these 2 points, and if there is no collision, then it permanently joins these 2 points. Let's say, for example, take randomly any 2 points, take this point 1 and your target point here. You see that if you try to connect point 1 to your target with a line, with a straight line, then there is an obstacle between them. Okay, so that's why the connection is not possible. So we don't connect these 2 points. Now take any 2 more random points here. Now let's say 2, 3, 4. Now take this point number 4 and 5 and try to connect them. So there was no obstacle here, so we have connected these 2 points. Okay, so this is now the path is, this path is shorter than the original one. So the original path from 4 to 5, okay, 1, 2, 3, 4, 5, 6, 7, and then you have a target. So the original path from 4 to 5 was not the shortest path, and then we made, by subdivide and reconnect, we have connected a straight line. Okay, this should be a straight line. It doesn't look like a straight line, but it should be a straight line. Okay, and this path is shorter than the original one, and we shall do this technique repeatedly. Take randomly 2 points again. Let's say this time the points were point 1 and 5, and then we see that if we connect these 2 points, this line is not in collision with the obstacle. So if there is no obstacle, then we just simply connect these 2 points. Okay, so now this is the shortest path from 1 to 5, instead of going from 1 to 2 to 3, 4, and then 5. Let's take more. Now in the path we have, this is the path S, 1, 5, 6, 7 to target or the goal location. Now in this new path, take any 2 points again and then try to connect them. Let's say we have taken the point 1 to 6, and 1 to 6 we see that there is no obstacle, no collision, and then we just simply connect it here. So now your path is from S to 1, 1 to 6, 6 to 7, and then finally to your goal location. So in this way, you can see that we have removed many jerks, many unnecessary portion of our path, and in this way you can make the path shorter and also make the path smoother as compared to the original path. So this was the main idea behind path smoothing by subdivide and reconnect. Okay, so previous method we have for path planning, we studied about there are methods that uses grid or graph, and there are methods that using some random sampling the nodes and then making a tree. So let's see a totally different and a new method called artificial potential fields. This method is inspired by potential fields in nature, like the potential fields, for example, the gravitational potential field, and also fields like electrical fields or magnetic fields also. So this method works on same principle. They are also sometimes they are called virtual potential fields because they are virtual. We create them virtually for the robots, but actually they don't exist. Okay, for example, the fields like gravity, electrical field, or magnetic field, they are the real fields. But this one, artificial potential field or virtual potential fields, they actually don't exist, but we model that, we model our environment like that, so the model mimics that there is a field that attracts a robot. So what happens when you put an object in a gravitational field? So we know that for example, gravitational fields, we have the potential, gravitation potential energy, we can say that P is a function of h, and this is equal to mass into gravity into height. So this is the gravitational field, this is the gravitational potential we have. And if you place any object in this field, for example, this is your Earth here, and you place it has around this it has a gravitational field, and if you place any point or object here, then this object will experience a force toward against this field. Okay, so if you want to calculate the force here, you have to take the F is equal to, this is partial derivative of this, your potential, and also there is a negative sign because the force is in the opposite direction. And if you do a partial derivative of this thing with respect to h, then it will be minus mg. So the force experienced by an object in a gravitational field will be minus mg. So this was a natural field, okay, and you can see that when an object experiences this kind of force in the gravitational field, it will start moving toward the earth, or toward the height where toward the ground where the height is 0, with a force minus mg. So we try to mimic same behavior for the path planning of the robot. We say that, okay, our robot is an object or a point, and it experiences a force toward the goal. Okay, what we do, we model a virtual field there that actually doesn't exist, but we mathematically model it like that, so the robot experiences a force. So here we say that we define that the goal configuration, the goal, your goal or your destination is assigned a low virtual potential, and obstacles are assigned a high virtual potential. So how we create this field is by assigning a virtual potential. In our environment, we have, let's say, this is our environment, and here you have a start point, and here you have a goal, and this is, let's say, we have obstacle here. So So what we do, we want to do a path planning. We want our robot to move from start point to goal point, but by using artificial or virtual potential fields. So how we can make here a virtual potential field. So we model it using mathematical equation, and here we say that goal has an attractive force which attracts the robot toward it. Similarly, like here we say that the Earth has a potential energy, a potential field, and in this potential field, any object will be attracted toward the Earth with a force minus mg. We do same thing here. We say that okay, our goal has some kind of attractive field, and robot will be attracted toward the goal with some specific force, which we shall model later. And the obstacle will have a repulsive effect on the robot. So what will happen when the robot experiences a force toward the goal, attractive force, when it reaches near the obstacle, it experiences a repulsive force here, and then it will try to navigate toward the goal. So there is a combined effect of attraction and repulsion. Okay, so the goal configuration is assigned a low virtual potential, and obstacles are assigned a high virtual potential. So yeah, so attraction for the goal, repulsion for the obstacle, and that's what we want. We want to avoid obstacles and we want to reach the goal. So that's how we can do that. That's how we can achieve that. Okay, we apply the force to the robot proportional to the negative gradient of the virtual potential that will naturally push the robot toward the goal and away from the obstacles. Similarly, that we did here for the Earth, there was only a traction force, and for the obstacle there will be also a repulsive force. So the attractive force will attract the robot toward the goal, and then there will be a repulsive force that pushes the robot toward the goal, and the sum of these forces will eventually guide the robot toward the goal. Okay, so what are the advantages of this kind of methods of virtual potential field or artificial potential fields? Why we do that? So see that with the grid and graph based planning, or even this rapidly exploring random trees or other methods, they have their own disadvantages. One of the disadvantages was when the number of nodes increases, it takes more time to calculate the path. But in this method, the artificial potential fields, as the gradient can be calculated very quickly. Gradient means slope, the partial derivative of your potential. So it's very easy to calculate, and it can be calculated also quickly. Okay, that's why these methods are faster to calculate to compute your path, or to avoid the obstacles, or in the execution time is faster. So the motion can be calculated in real time, so they can be used for the reactive control. Okay, no planning is needed, just in real time, when you see the obstacle, you just try to avoid it, and so there is no planning is needed in advance. So if you remember from the previous lecture, we studied about the reactive and control, and then There were controls where you need planning also. So this particular method for artificial potential fields, they can be used for reactive control in real time because the gradient can be calculated very quickly. So you can see that this method is fast as compared to other methods. One other advantage of this method is that it can handle moving obstacles and also obstacles that appear unexpectedly. So moving obstacles and obstacles that appear unexpectedly. In real world scenarios, you see that the obstacles are always moving. For example, the cars are moving, there are people, and if you go out with your car on the roads, you see that everything is moving. And so the previous methods that we have discussed, like grade-based methods or graph-based methods, they assume that the map is fixed and the obstacles are all fixed. So this is very ideal situation, but in actual real world scenario, this is not possible. The objects are moving and sometimes the map is also changing itself. Okay, for example, let's say you're driving on the road and suddenly there is an obstacle, there is another car comes in front of your car, or a person comes in front of your car. So this will be a moving obstacle. And then there are some obstacles that are not expected. For example, you have a map of the environment and then you know that where are the obstacles, and then suddenly the map changes. For example, there is a car that just came inside the map, but when you made this map, the car was not there, and now you are path planning and you see that there is a new obstacle which was not expected. So this is an unexpected obstacle in the map, so you didn't model. So these kind of algorithms, for example, the artificial potential field, they have, because they are very reactive, very fast, they can do this obstacle avoidance and path planning in real time. They can handle this sudden changes in your model and also in your environment. But if you see the A-star algorithm, which uses a fixed map, this type of algorithm, they will fail in this kind of situation where the environment changes or where there are moving obstacles. Okay, now we have seen the advantages of artificial potential fields. There is also one disadvantage. And the disadvantage is that it can get stuck in local minima. Now, what is local minima? Local minima is something like should draw it here again. This was a goal here. Sorry, this was a start point, and this was a goal. And here we said we have obstacle here. So we say that, okay, our robot starts from here. Let's say this is our robot. And it is being attracted by the goal. So it will start moving toward the goal, and it is being repelled by the obstacle. Okay, this is obstacle O. So these two forces, they are against each other. So goal has an attractive force, and then your obstacle has a repulsive force. And also at the goal, your potential or your force becomes zero. Okay, it's the same like on the earth, in the gravitational potential field. When something is on the when its height is 0, or when it's on the ground, the force is almost 0, or you can say it's cancelled by the repulsive force. So here you can say that there are some scenarios when the force, the attractive and the repulsive force, attractive and repulsive forces, they are equal, and then the net force becomes 0. And then your robot think that, okay, here we have our goal point is reached. So this is a local minima, you can say. This is not the global minima. Global minima is actually on near to the goal we have. So this is a problem with this kind of method, that your robot will stop somewhere here, because the two forces, the attraction and repulsive force, has cancelled each other, and your robot thinks that the goal is reached, but actually the goal is far away. So this is something called local minima. If you want to know the concept of local minima is something like, imagine a hill. This is the mountain, okay? This is the mountain, and you are on the top of the mountain here. So this is a person that is on top of the mountain here. Okay, now this person wants to go on the ground, where they get away from this mountain, okay? And so how they can detect that? How they can detect that now the ground has been reached? So the person start moving downward in this direction, and when it reaches here at this point, okay, so it may think that this is it, the person has reached the ground, or the lowest level, okay? But this is the local minima. Actual minima, or the minimum height, is here, or in this line here, from here to here. This is called the global minima. So yeah, this was the difference between local minima and global minima. So same thing is true for the robot, okay? So yeah, these were some advantages and disadvantages of this method. Actually, this disadvantage should be at the end, but okay, but I hope you understood. Yeah. So now let's see in some detail that how we can model artificial potential fields to work as a path planner. So the first thing is, we assume that the robot as a point in your C space. A goal configuration is typically modeled as a quadratic function of potential energy with 0 at the goal. So now we want to make a function that represent the virtual potential field, okay? And so in most cases, the easiest way to do is using a quadratic function. And what we do here, that we say that, okay, we have a potential which is P, and P of Q, and this is equal to 1 by 2 q minus q goal, and then k q minus q goal. So we model our artificial potential using this quadratic equation. As you can see, when these two terms will be multiplied, they will become square. So this will become a quadratic equation. So anything with square, it is a quadratic function. Okay. So where K is a symmetric positive definite weighting matrix. It can be an identity matrix also. So this thing is similar to, if you remember, we in the previous slide for the gravitational potential, the gravitational potential was mgh, mass, gravity into height. Okay, but that was not a quadratic function. But our virtual potential P is a quadratic function where Q can be any position, and Q goal is your goal location, where your goal is located. Okay, and this function, this potential function, it will give 0 value at your goal. So it will look like this. If I draw it here, this function will look like some, let me change the color. Okay, if I draw this function, it will look like this, something like this. This is the quadratic function, okay? And here your goal point will be located here. And this will be your PQ. So this is a quadratic function. This is a graph plot of quadratic function, and your goal will be located where your function becomes value 0. Okay. So this is how we model a virtual potential. This is also, if you see that, if you want to observe or relate with the gravitational potential, it looks like a, you can see, or you can say, if you put a ball here, at this point you place a ball, so let's say if you place a ball here at this point, this is my ball here, okay? So what will happen? The ball will experience a force here in this direction, and it will start moving downward. It will reach here, and then it will finally stop here at the goal. If this ball, it experiences this potential force, okay? The ball will move from this height to the lower height, and then it will stop here at this goal. So that's what we want from our robot also. We want that the robot should stop at the goal. That's what we want. Okay. If the robot is away from the goal, it should start moving toward the goal step by step till it reaches the goal position, and then it should stop there. So this curve of attraction force, we model it using this quadratic potential function. Okay, the attractive force induced by a potential field. So the potential field that we made here, this PQ. So now we want to calculate the force that will be experienced by an object in this potential. So this force will be, let's say, F goal of Q is equal to, this is, we have already mentioned that this is force is always negative. Partial derivative of P goal and if you do a partial derivative and then this force comes out as Q goal minus Q. So if you place an object within a virtual potential that is quadratic function, so this is a potential that we developed in the previous slide. This was a quadratic function. The goal is located here. So whenever there is an object here, it will experience a force which is F goal, and this force will be negative, of course, and this force will be towards the goal, and this force will always be attractive force that attracts this object toward the goal. The value of this force will be the partial derivative of the potential function or the virtual potential function, and this comes out as K multiplied by Q goal minus Q. So Q goal is location of your goal and Q is location of your object. So that's how we make artificial attractive potential or artificial potential force that attracts the robot toward the goal. So if you see in your actual this workspace or your configuration space, so if this is your start location and this is your goal location, so when you model this environment using this equation of potential, quadratic potential field, then what will happen if the robot is here at this location? So it will start experiencing a force which is F goal, so it will experience a force toward the goal, and the value of this force will be F of Q, and so based on this force the robot will start moving toward the goal, and when it reaches the goal then it will stop. So this is the actually what's happening in the real world, okay? But in the virtual, because this force in reality does not exist, okay? This is not like a gravitational force or magnetic force or the electrical force. This is a virtually or artificially created force. How we created it? Using a mathematical function or a mathematical potential field that looks like a quadratic function. So we use this quadratic function because it's easier to because it has one minimum point, okay, that is at 0, and it's also easy to take a derivative of it. So whenever you, at any point when you take a derivative of a quadratic function, for example at this point, a derivative points out in this direction. At this point the derivative points at this direction. At this point that the derivative will be at this direction. So so for this potential function we take derivative and we the object or the robot will always move in the negative direction of this. So if your robot is here, your robot is here, it will move in the negative of this partial derivative. Okay, the derivative is in this direction and the robot will move in opposite direction, negative of this. So it will move here and then here, and then finally when it reaches the lowest point, then it will stop. So this is totally mathematical. This field in actual doesn't exist. We create this artificial potential field by purely some mathematical function using quadratic function. And the advantage of this is that when we apply this in the robot, in the real environment, the robot acts like it is experiencing some kind of force that is attracting this robot towards a goal. Okay. Okay, now in the previous slide we have seen the force of attraction only, because we haven't considered obstacles. We said, okay, there was a goal location and the robot is attracted towards a goal. But in actual, there are some obstacles also in the environment. So how can we model these obstacles or the repulsive force? The repulsive potential induced by obstacle O can be calculated by the following formula. So to model the repulsive force or the repulsive potential, we use this formula P of Q. This is obstacle, we say, okay, PO obstacle is equal to K over 2 d square. So here the K is a scaling factor and its value is usually greater than 0. And the d is a distance between your present location and the obstacle. Okay, so if you have a distance to the obstacle, and also you have a scaling factor, then also you can calculate your repulsive potential. So once you have this repulsive potential, you can calculate the force induced by this obstacle potential or this repulsive potential, and this force will be equal to F of obstacle or the location Q is negative of potential gradient PO PQ, and this will be K PQ P cube, and then you have partial D over partial Q. The total potential is obtained by summing the attractive goal potential and the repulsive obstacle potentials. So till here you have found the repulsive potential. So similarly, I would like to give the same example here. So when your robot is, this is your start location, this is your goal location, and here you have obstacle here. So your obstacle will have a potential field, okay, and this potential field will exert a repulsive force in all directions, while your goal location will have an attractive force. So this force can be calculated using this equation, and whenever your robot will go near this obstacle, it will feel a repulsive force and it will start moving away from the obstacle, and it will start moving toward the goal. The total potential is the sum of attractive potential and the repulsive potential. So if you want to find the total potential, that will be equal to your P of Q is the sum of goal potential plus the sum of all the potentials of all obstacles. Let's say there are I obstacles in your environment, then there will be I, each obstacle will have its own repulsive potential, and then you have to sum all of them. So this will be your repulsive potential, and you have to add it with your attractive goal potential. And similarly, you can calculate the sum of attractive and repulsive potentials, and keep in mind that this may not give a minimum zero force at goal. This is also possible. Although our goal is located at the minimum attractive potential, but when we add the repulsive and attractive both, then it's not necessary that they will always be zero at the goal. So the force, the total force F of Q is equal to F goal plus sum of all obstacles So this will be the net force experienced by your robot in a real world where there are obstacles and there is goal. So this will be the force that will be experienced by the robot. To control the robot using calculated force, we can either use these types of equations. We can use this U is equal to, this is the net force experienced by the robot in the virtual potential field. And so what is the B? B is a positive definite so this term here, it will give you, it will have a damping effect on your motion. So this will have a damping effect, and this is your original force. So, and this is your control law. So this is the output that is given to your robot, so it can move. Okay, if B is positive definite, then it dissipates energy for all when this term Q dot is not equal to 0, which will reduce the oscillations, and it will also guarantee that the robot will come to rest eventually. But if the B is equal to 0, then the robot continues to move while maintaining constant total energy, which is a sum of the initial kinetic energy and the initial virtual potential energy. The motion of robot under this control law can be visualized as a ball rolling in gravity. Yeah, it's the same example that we have given previously. So So let's say your robot is here at this point. So when you apply this control law here, where you add force and you're damping also, so it means that whenever your robots want to move, it also experiences some damping force. Like in the real world, when a ball moves from a higher point to a lower point, it also experiences friction. Okay, so the friction actually slows it down. So same thing we are doing here. We are adding, with our original force, we are adding some damping or friction, and so it can mimic the behavior of, our robot can mimic the behavior of a ball that is under the influence of gravity, rolling down till it reaches your goal point, or the minimum of your potential. So this is the one way of doing calculating the control force. And the second way is to directly use your treat the calculated force as a commanded velocity instead. So whatever you have, the force you calculated, F of Q, attractive plus the repulsive force, you treat it as a command velocity and give it to your robot. So this will automatically eliminate the oscillations, and your robot will start moving toward the goal till it reaches the goal.